welcome. Is okay? To the first of a new series, and something that has started the museum on a little bit of a new trend of lectures about how computers are used to help people. And this is, when we started several years ago, we mainly collected hardware, and everyone said to us, well, where's your software? And the last lecture by Alan Perlis told us that software was a soap bubble. So now we don't have to collect software, but we do have something, I think, wonderful and new in collecting machines and some of the applications of how computers have been used. And one of the working exhibits in the museum is a Kurzweil reading machine. And after the lecture, that will be demonstrated for any of you who have any curiosity about it, about 15 or 20 minutes after the lecture. And we hope someday to have something demonstratable from what Dr. Petrofsky has. I don't know what it would be in the same way. So that's really a wonderful new addition to the collections of the museum. And with it, because with our collections, we have these talks that are videotaped, so that not only do we have the machines, but we have somebody who built the machines, who started the field, the real pioneers. And so this is the first of the talks about applications, and it's sponsored by co-sponsored with the museum by one of the technical groups at Digital. And Ruben Olscher, who is our co-sponsor, will introduce the speaker.
Thank you, Gwen. Outside of the museum, Gwen and Gordon, Kitty and I meet in Brazil, Australia. It's nice to do it in Marlborough. I would like to say on behalf of Bill Long, our Vice President of the Technical Group, who really was the one who initiated this as a co-sponsor with the museum, considering the fact that we have had the opportunity at Digital of working with leading scientists in applications, developing things for not only the type of thing that we have for our first and initial speech today in the first lecture in the series, but the great applications of mankind that are coming out of the new technologies of computers. And if I can express for Bill, who unfortunately had been asked by his doctor to stay off his back for about 5 days, nothing serious, to express his excitement and enthusiasm for the meaningfulness of Digital as a corporation, not only as a business, but as an opportunity for the people who work here and work with the technologies to deal with the great and leading scientists of our day. It is something that doesn't come in a paycheck, but it's something that means a great deal to all of us in the technical group. And on behalf of Bill, I want to express the importance to us of this new series and this particular lecture series. For the first and the initial session, it's very apropos that we have Dr. Petrofsky, who for 13 years has been involved not only with his great science, but in working with computers. He's executive director of the National Center for Rehabilitation and Engineering, and he has received national attention for his pioneering research in computer-simulated rehabilitation for paraplegics. I think if you, on the way in, have not had an opportunity to see some excerpts from the CBS 60-minute show where he got national attention, as went out, and also he was on ABC Good Morning America. I think this is a very exciting new first. And I would like to just quote from a Sunday supplement, Dr. Petrofsky. They say some interesting things about the gentleman. I will also say that he meets one of our criteria of the profile for great scientists. They are unpredictable, or they produce unpredictable things. Kitty and I were to meet him at the Marlborough Airport, Chris found out that he was coming to Worcester Airport, but we're happy that he drove over here and met us today. The heading here is what he's doing is called biomedical engineering. It's an exotic marriage of biology and high technology, and I think that's a very nice head. Let me read just one or two paragraphs and let Dr. Petrofsky have the podium. He works all day with what he calls leading-edge technology. Then he goes home to listen to Glenn Miller or to tinker with his World War II era walkie-talkies. He deals with microcomputers smaller than your thumbnail, but he has a special fondness for the first computer he ever used, an aging steel panel machine the size of a Victorian wardrobe. He has studied the effects of weightless exercise on astronauts' hearts, but he flies with the Confederate Air Force, an organization devoted to his preservation of vintage aircraft. His name is Jerrold S. Petrofsky, and he lives in a time warp where the future is unfolded into the past. Petrofsky is director of the Biomedical Engineering Labs at Wright State University and an associate professor of biomedical engineering and physiology. If his name sounds familiar, it's because he's appeared on 60 Minutes, Donahue, Good Morning America, and network news shows all over the Western Hemisphere. He has been acclaimed as a worker of miracles who hopes to free people from their wheelchairs. In November, he demonstrated a computerized system he is developing that returns motion to paralyzed limbs. He and his test subject, Wright State senior Nan Davis, we'll talk about today, became an instant international celebrity when she stood up from her wheelchair and walked for the first time in 4.5 years. Petrofsky is a serious scientist. He worries that every day he spends courting research grants or humoring the news media will mean another day millions of people will have to languish in wheelchairs. But inside the time warp lives a child in Jerry Petrofsky, the boy tinkerer, and I love this, who enjoys researching the human nervous system just as he enjoyed futzing around with radios and TV years ago in St. Louis. Dr. Jerrold Petrofsky.
Thank you. Oh, thank you. It's a pleasure being here this afternoon. And, gee, I think that's not functional anymore, or close to it. Well, it's working. I can stuff it back together. If I have the slide projector on, please. Certainly a pleasure being here this afternoon to be able to show you a little bit about what we're doing. I have a personal and very special fondness for digital equipment because digital equipment was the equipment that I learned on when I was an undergraduate student and first started working with computers, with digital hardware, with a digital desktop trainer, and with the Link computer. I've really been impressed this afternoon to see the Link you have in the museum. It's so clean compared to mine. Mine now is was built, I guess, by you folks in '59. It brings it on 24 years old, going on 25. It's a little bit dirty, but still quite functional. It still works. It's serial number 3 from the factory here. And so I have a very special fondness for this particular type of equipment. Most of the decisions I've made over the years about which microprocessors to use for this system were based on my experience with the Link. Originally, when micros first came on the market, for example, I went to an Intel 8080 system because the programming language was so similar to the original Link language compared to, I guess, the Motorola, which was more similar to the PDP-8 language. And since I never had the exposure to the PDP-8, all my microprocessor selection was done on the basis of that original Link language and my original Link training. But basically what we're doing at Wright State and really a number of other places around the world, it's hard to really begin to give you an idea of the number of people involved. If I have the next slide, please. Next slide, please. There's a large number of people involved in the project, perhaps at this point, 50 to 75 MDs, 75 PhDs, and several hundred lab technicians around the world, all centered around working with us at Wright State on a process or a technology called microprocessor control movement in paralyzed muscle. Next slide, please. And what I'd like to do over the next hour is try to show you what this is all about. You know, one of the things you like to do, I remember when I was a graduate student, and I guess graduate students are always very naive, even more so perhaps than undergraduates, or equal. One of the real problems you have is that you think When you come up with an idea, it's the first time you've ever heard of it. You've come up with something new and unique. Well, I like old books and I like old things, and I was rummaging around an attic about 4 or 5 months ago, and I ran across this. It's an article written by a person who taught engineering 2 days a week and medical school 3 days a week, and some of his students asked him to write a little paper on a new technology called electricity. So what he wrote is, "But what is the usefulness of electricity? For all things must have a usefulness, that is certain. Since electricity must have a usefulness, and we have seen it cannot be looked for either in theology or in jurisprudence." He hadn't thought of the electric chair, that came later. "There is obviously nothing left but medicine. The best effect would be found in paralyzed limbs to restore sensation and reestablish the power of motion." That's not a misprint. That was published in 1744. So in 1744, somebody had the idea of using electricity to allow paralyzed people to move again. What happened? The problem is the complexity of the whole thing. That's what's taken all this time. There's 600 muscles in the body. To stand and to walk requires coordinating all those muscles at the same time, and they have to contract and relax at different times and by different amounts to allow us to have posture for standing and walking. That's a massive computing problem, and it's something that wasn't soluble until later time. Next slide, please. The real thought for using electricity to stimulate muscle came from Galvani in 1791. Galvani said that nerves conducted electricity. He used a very simple experiment to prove that. He took a metal rod, and connected it between the spinal cord and muscle of a frog, and the frog muscle jumped. So he said that the spinal cord conducted electricity. Well, it was a good experiment in the fact that it was correct. In terms of experimental procedure, it was terrible. What happened was he used a metal that poisoned the spinal cord. Volta pointed that out 25 years later, redid his experiment with platinum and silver, and found out that the spinal cord really was associated with electricity. You had something called a nerve impulse that was an electrochemical wave, and that electricity was intimately involved in the process of standing and walking. Next slide, please. People in the East began to take this very seriously, and they developed technologies called electroacupuncture. Nobody really knows for sure right now just how much science there is. There appears to be a lot of very good neuroscience and neurobiology involved in electroacupuncture in terms of changing neural pathways and changing feeling, lowering blood pressure and things like that. But it'll be a number of years, I think, before we in the West really understand that particular technology. Next slide, please. Unfortunately, people in the West didn't take things so seriously. In this particular slide, for example, this is a situation in the 1800s. The gentleman who's seated in the chair here has advanced heart disease. He's had several heart attacks, and to cure that heart disease, he's sitting down on a steel plate, and there's another steel plate on his head, and this is connected up to a Windhurst machine, generating about 10 million volts. Well, it took care of his problems with heart disease, because he never had that problem again. Unfortunately, electrical stimulation, the whole idea of using electricity to do anything in the body, anything associated with healthcare, began to be thought as just quackery. In fact, this slide came from the Smithsonian, from the National Museum of Medical Quackery. So nobody wanted to really work with that area anymore. It just died away. And in the West, electrical stimulation died from 1900 until about 1950 as a technology. In fact, even though computers and computer technologies advanced so much with electrical stimulation in the body, there's still a lot of skepticism in the medical community about we've had electrical stimulation for 150 years. It hasn't done any good. What can be done now? Next slide, please. The history of electrical stimulation becoming functional in the body. And electrical stimulation is often abbreviated with the term FES, functional electrical stimulation. The whole history of FES being applied to clinical medicine came about in parallel with the development of computers. Computers like this Whirlwind really are where I like to start my discussion of computers, because this was a 1948-49 vintage, which is my vintage. And from this machine on forward, the development of the computer paralleled what happened in medicine. Next slide, please. The first machine I began to work on was the Link. I've had a number of people from digital who have seen this thing say, "Did we make that?" You folks sure did. Back in 1959, 1960. That's a classic Link computer still in operation in my lab. And that's the machine I started to work on as a transistor and vacuum tube hybrid type computer, or mostly transistors with most of the vacuum tubes in the control console. It gave me a way of taking data from the laboratory into the A to D converters, processing that data, making decisions, and then controlling things in the laboratory, setting up an experiment on controlling motion using a digital computer. Next slide, please. This is some of the interior of the Link. Mine just isn't as clean as yours is. It's kind of a yellowish metal-looking color. Next slide, please. And it was really from these early developments of the early transistor computers that people in medicine began to realize that you could use computer technology, that using a computer in a laboratory environment, and the Link was one of the first chances we had to have a computer in a laboratory with us, rather than doing something online, where you could work in real time. You could handle a number of medical problems by data processing in real time. Next slide, please. You know, obviously, as these devices became smaller, next slide, please, and went down to the eventual microprocessor size, the technology far exceeded medical developments. From 1959, when the Link was developed, to current large-scale and very large-scale integrated circuit technology, suddenly we came to a point from not being able to control movement because we didn't have the technology and data processing to do it, to the point now where, at least in my opinion, we have all the data processing we need. The computers at this point in time and microprocessors are sufficiently fast and sufficiently small and have a sufficient low power consumption to handle a lot of medical needs, including walking or hand control. The problem now is software. It's learning how to interface these machines to the body. Next slide, please. Well, to give you an idea what this problem is all about and what's taking so much time, I'd like to start with just a basic explanation of what happens when you try to stand up and move or just lift your leg. When you think stand up and move, a thought originates in the brain. That thought starts as an electrochemical wave we call a nerve impulse or action potential. That wave travels down the spinal cord through connecting nerves called interneurons. These act like telephone cable. These nerves connect to other nerves called alpha motor neurons. These are called the final common pathway. It's the final nerve going to the voluntary or skeletal muscle of the body. So essentially, movement, in terms of going from the brain outward, is a three-part system. Thought starts here, it travels through connecting nerves, and goes out to the rest of the body. Now, obviously, it's a much more complex system. In fact, in terms of engineering, it's a very good closed-loop system exhibiting both positive and negative feedback control. It's also a nonlinear control system, which makes it by nature very complex. But basically, this is the basic elements of the system. With spinal cord injury, you damage the spinal cord. Well, what most people realize is the spinal cord really isn't physically damaged in a way that you can see. Most type of spinal cord injury involves something called bruising. With bruising of the spinal cord looks normal, the anatomy looks normal, the blood supply looks normal, it just stops working. You can have impact on a rib by falling or hitting something or just bending up and breaking a small blood vessel, and the spinal cord will stop functioning. It'll stop functioning for the rest of somebody's life. There's no physical damage you can see, nothing you can repair, it just stops conducting electricity. There's some theories about why that happens in terms of damage at the molecular level to the spinal cord membranes. But nobody really knows for sure why it stops working. But for 80% of the people in wheelchairs, there's no physical damage to the spinal cord. It just stops functioning. So the communication's been damaged from the brain to muscle. People in wheelchairs have a normal brain function if it's caused by spinal cord injury, and they have normal muscle and normal bone. It just stops being used and stops working. Because of that lack of use, muscle gets smaller and wastes away. Another big misconception people have about spinal cord injury is that that's the problem with their body, the injury to the spinal cord. In fact, that's not the problem at all. That's the primary problem, but not the real problem and hazard about being in a wheelchair. That primary injury will cost roughly $100,000 to $200,000 in medical costs for the initial hospitalization. Throughout their lifespans, currently, the average person who gets a spinal cord injury this year will have their medical coverage pick up approximately another $1.3 million in medical care for the rest of their lives. The reason for that high medical care is secondary problems. When you stop using muscle, it wastes away. Bone gets so paper thin that simply lifting somebody's leg up who's been in a wheelchair for 5 or 10 years and trying to move it can break the leg. And some people, bone just gets paper thin. The heart deteriorates, lungs deteriorate, there's bladder and kidney problems. The whole body goes into a very low key. It's like one of us, for example, laying down in bed for 6 months, not getting up and trying to jump up and run the marathon. You kill yourself. Well, for someone in a wheelchair, the primary problem is the spinal cord injury. But in fact, the problem they have medically is all the complications associated with that. One of those, for example, is pressure sores. When the muscle wastes away, bone surfaces protrude and get very close to the skin. So sitting in a chair for a long period of time, that can cut off the blood supply and cause something called a pressure sore. It's a sore that starts from the skin and goes all the way down to the bone. It's very, very, very common for people in wheelchairs. It costs, if they have to be hospitalized, which is most of the case, for a large pressure sore requires hospitalization. It costs $100,000 to $200,000 to heal each pressure sore, and they can happen as often as every few years in some people. Every time someone gets a pressure sore, a massive pressure sore, it's been estimated it cuts about a year off their lifespan because of damage it does to the kidneys and liver. So it's these secondary diseases that result from not using muscle, the real issue with spinal cord injury. So when you begin thinking, what can you do to try to make someone stand up and move again? There's two problems. One is controlling movement. The other one is allowing people to be built back up again. Next slide, please. With that, then, what I'd like to do is address 4 basic areas. Methods of controlling movement. How can you control movement? The body is not a robotic system. If it was a robotic system, the problem would have been solved years ago. With a robotic system, you have servo motors. The motors cause an artificial limb to move and to rotate. Given a certain amount of current, the motor is going to behave in a certain way. And you put sensors out there so that you know what's happening. You have linear control models in terms of your equations, and you control movement in the robot arm. Well, the body isn't quite that nice. To begin with, the motor is not a motor at all. It's flesh. And the properties of that motor, how fast it moves and how strong it is changeable by things like physical training, muscle fatigue, muscle temperature. For every 3 degrees you change muscle temperature, you double the velocity of contraction of muscle. Genetic differences in the muscle. Not only that, but those muscles are hooked up in funny ways. You don't have a single muscle that will cause the arm to go like that. Most of the muscles go across joints. So if you contract one single muscle, the joint rotates. It never goes straight. So in order to lift this arm up, you have to use several muscles to stabilize the arm, plus the fact that that muscle connects up to here, and when you try to lift your arm up there, it puts tension on your collarbone, which moves your shoulder, so you have to use other muscles to straighten your shoulder, but those muscles are connected to your hip, which means you turn your hip, so you've got to straighten the hip up, but those muscles are connected to the legs, so you've got to straighten the legs up. So you've got a massive 3-dimensional control problem trying to make anything move in the body. That's the reason Kruger's original idea in 1744 has taken so blasted long to do. From the engineering standpoint, it's a massive closed-loop control problem with totally nonlinear activators. Even if you can get control of movement, another problem you've got is decoding the thought process. Because if you can use a computer to make somebody lift their hand up and move it, suddenly you've got the massive problem of determining what they're thinking about doing, having the computer use some type of keying system to understand what they want to do to make it happen. The rest of the problem then is rebuilding the body. Principal problem we've seen is bone, but also stress in the body. Go back to the original thing I was talking about a few minutes ago. You have a car, you haven't used it in 5 years, it's been sitting in the driveway, you run out and start it up and try to take off and go down the street. The engine will blow up. The transmission will break. You'll throw push rods through the top of the engine. Things have to be brought back very carefully and gradually to a healthy state before you reactivate the body using computer control. Next slide, please. Well, in the body, we use something called proportional control. That means that muscles don't contract fully, they don't relax fully. There's something in the middle. You don't have your arm here or here. You can have your arm there or there or there. And all the different muscles contract by different amounts. And those proportional control equations prove to be the hardest part of the project. Next slide, please. This work was originally started on a digital desktop trainer and later followed up on a Link computer from 1969 for about 11 years. It involves setting up a closed-loop system. Like any engineering closed-loop system, you have something stimulating the muscle. That causes the muscle to move. You then have a sensor showing that movement. That sensor tells the stimulator what happened. So it becomes a smart stimulator. The stimulator knows what happened and then does something to correct it to follow a program of movement. Next slide, please. There's a lot of people that have worked over the years with open loop control. By that I mean there's no sensor. You just stimulate the muscle and it jumps. You can get open loop control very easily and make the muscle move. If you go over to a lamp on the wall, unscrew the light bulb, wet your fingers, stick them in the socket, you'll get open loop control, and you'll get a great deal of movement. But closed loop control means doing it very precisely and accurately, and that gives you the advantage of coordinating movement, minimizing muscle fatigue. One thing you don't think about is balance. Balance is a very nasty thing to have in the body. With a closed loop system, if you know the position of the body in 3 dimensions, you can give somebody balance so they can't trip. By detecting fatigue, you can warn somebody that they're going to fatigue. That would be like setting up a system without knowing fatigue is like going out and driving your car around and taking a wire cutters and cutting off your gas gauge. If you don't know when you're going to run out of gas, you can get into trouble very, very quickly. So detecting muscle fatigue and alerting somebody about that fatigue is very important for a practical system. You can also reduce the stress on bones and joints. One of the key issues we worry about is inducing arthritis, arthritic spurs inside the knee joints. There's a condition called Charcot joints that scared us continuously over the last number of years. There's a condition, Charcot joints is sometimes called anesthetic knee. What it means is that some people with certain diseases can't feel their knees. They're not paralyzed, they just can't feel their knees. With anesthetic knee, when they walk around, they keep locking their knee too hard, and the knee eventually breaks down and crumbles. And that's it. They spend the rest of their life in a wheelchair, or they have to get artificial joints. That's a common clinical condition with a number of diseases. With someone who's spinal cord injured who also can't feel their knee, you've got to make very, very sure that when they stand up and walk, you never, ever hyperextend the knee. The knee can never come to a full lock, and when the knee approaches a lock, it has to have its velocity reduced, so it's a very soft lock, so you never overstress the knee. Or you'll induce that condition, and you'll have somebody walking, but only for a very, very brief period of time before clinically they'll never walk again. So basically what we're looking at is a very complex problem. Next slide, please. And if I can have the 16-millimeter projector on the 35 off for a moment, please. Let me show you what closed-loop control looks like. 35 off for a second. Okay, this is a paraplegic. He's paralyzed from just about here on down. He's holding his leg up under computer control. There's sensors here on the knee. There's weights on his ankle. When I push down on his leg comes back up to the original position. You'll also see what looks like tremor in the knee, with the knee coming up and down a little bit. That has to do with the sensitivity of the sensors. When the muscle starts to fatigue a little bit, the computer brings the leg back up again. So it almost looks like human tremor. And in fact, that servo loop error, as it's called, is set at the same frequency as human tremor. So the movement looks very, very natural. With the computer off, that leg would fall. He's holding it in position under computer control. And that's basically what closed-loop control is all about. It looks fairly simple, but in fact took a lot of years to develop. Most of the work was done in laboratory animals, represented about 11 years of work, to come up with the first practical closed-loop control equations that self-compensated for muscle fatigue, changes in muscle temperature, and changes in the load to allow that very simple experiment. And slide on, please. Next slide, please. Well, once that technology was developed, what we decided to do was change the technology from animal experiments involving closed-loop control and some human experiments decoding the thought process to trying to make a paralyzed human being lift their leg up and down. Now, to do that, we used a closed-loop stimulator system. The first system looked much like a weight training system. In fact, that's exactly what it is. It's a chair. Someone sits in the chair. There's an ankle bracelet, and they try to lift their leg up and down with the ankle bracelet going through a steel rod onto some weights. There's a sensor on the weights showing the position of the weights and hence the position of the knee. In that manner, then, the computer monitors the knee to try to have them move their leg up and down. Now, bear in mind that's something very simple for us to do, but this is a paralyzed human being. With the computer off, she can't move a thing. And if I can have the 16 back on again, please, and the 35 off. This is a quadriplegic. It's a C6, C7 quadriplegic. That means the damage is in the neck. You see electrodes on his legs. The electrodes are connected to the computer. The computer goes through a program of very gradually bringing up the voltage to have the leg move through a profile of movement, to try to have the leg move up slowly and down slowly. In health spas, you call that isokinetic exercise. It's used for strength training. Because the first thing we wanted to do was find out if our animal control equations would apply to people and also start building the body back up to health again. And the fastest way to build strength is progressive resistance exercise, or isokinetics. Notice how smooth the control is. It's not like just putting 2 electrodes on somebody and having the muscle jump. And projector off and 35 on, please. Next slide, please. Well, that system proved to be very good in terms of strength training. I'll show you some of those results in a few minutes, but the results were much, much better than we ever expected to have. Tremendous gains in muscle strength, but very little in terms of cardiovascular fitness, very little in terms of the kidneys, very little in terms of the lungs, and some changes in thickness of bone, but not a whole lot. But if you think about it, if you want to get in good physical condition, you use isokinetics for weight training, but to build your heart and lungs, you do something called aerobics. Aerobic exercise can involve dancing, running, it can involve swimming, it can also involve bicycling. Bicycling was ideal for us because it allowed us to do 2 things. First of all, in the footage you just saw, we had a quadriplegic lifting 1 muscle up and down, single muscle control. In this case, with a bicycle, we could go to multi-muscle control, have 8 different muscle groups on the legs connected up to the computer, or as few as even 2 muscle groups, and have the computer follow a profile looking at the position of the hips, knee, ankle joints, sensors on the bicycle pedals, so that a quadriplegic or a paraplegic could pedal a bicycle to build up their heart and lungs and to build endurance for muscle. Obviously, the bicycle had to be modified because quadriplegics, for example, have no posture. So it has a high back seat, breakaway shoes like you'd have for skis, so if somebody has a spasm and their leg starts to move in a bad direction, the foot can come off the pedal and they won't be injured. And I can have the 16 on again, please, and the 35 off. This is a quadriplegic, C5, C6 quadriplegic, pedaling the bicycle at about 15 kilometers per hour. Again, remember, he's paralyzed from the shoulders on down. But in fact, this particular technique did allow the heart to be built up, lungs, bone, and muscle very nicely. And we could take people who were paralyzed as long as 20 or 25 years and bring their bodies safely and efficiently back to health again. Also, it demonstrated multi-muscle control in real time using the computer. A lot of the sensors you see were redundant. The sensors on the hips and knees, for example, really aren't necessary for bicycling. They're redundant in the respect that the pedal sensors show the same information. So the system's gotten much simpler now. And I can have the 35 back on again, please. Next slide, please. To give you an idea of some of the benefits of bicycling, for example, if you look at somebody's blood pressure who's a quadriplegic, the average resting blood pressure of a quadriplegic, could you focus that in just a little bit, please? The average resting blood pressure of a group of 4 of our quadriplegics was about 72 millimeters of mercury when they came into the lab. In most quadriplegics, the blood pressure can be very, very low. In quadriplegics, for example, there's so much damage to the heart and to the cardiovascular system that many quadriplegics can't sit up. If they sit fully erect, they pass out. And if you change their body position rapidly, they can go into shock and die. So there's a lot of problems with the cardiovascular system. And we brought people in, they had very low resting blood pressures, and blood pressure during exercise was very unstable and went very high. After training on the bicycle, resting blood pressure went up toward normal. Exercising blood pressure came down, and blood pressure became very stable. They could tolerate changes in body position. This was after about 2 weeks of training on the bicycle. So their bodies became adopted, they became healthy again, and they could tolerate changes in temperature, they could tolerate changes in body position. It really was a very good device for building up the heart and the cardiovascular system in people who had been in wheelchairs for very long periods of time. Next slide, please. One little offshoot of this thing was, well, I suppose in industry you have the same thing you have in universities. At the end of a budget year, the last few weeks, money is a little bit tight. And we were a little bit tight the last 2 weeks of our budget year last summer. And we didn't really have the money to go into any new projects. And so we tried something a little bit different. Next slide, please. Huffy Bicycle Corporation is a Dayton company, and they donated a three-wheel bike. We had some spare pieces of wood and metal around the lab and built a microprocessor. Can I have that focus just a little bit, please? We built a Z80-based microprocessor with 2K of EEPROM and 2K of RAM on the Z80, rechargeable battery system, sensors on the pedals, breakaway pedals, the same type of seat that you saw on the other system. Using that system then, with analog to digital converters from the handlebars providing information from the subject about how fast he wanted to go and things like that, we developed a portable outdoor tricycle for people that are wheelchair bound. I can have the 16 on, please, and 35 off. This is a paraplegic now. We're putting her on the bicycle. You can see the electrodes on the legs. Most of the other electrodes can't be seen. They're under her clothes. And using hand controls, she can change her speed and pedal around campus. Again, remember, she's paralyzed from the rib cage down. She can't feel her legs. She can't control her legs except on the bicycle with its onboard computer. And 35 back on, please. Next slide. Well, obviously, what we were leading up to was developing the control to be able to have paralyzed people stand and walk. That's where things were leading, building the body back up again and trying multi-muscle, three-dimensional control in real time on the computer. Next slide, please. There are a couple of problems. If you take someone who's paralyzed or someone who's had a stroke and they begin to have a return of muscle function, the process is really fairly simple. What you do is you take them into a rehab center and they have parallel bars inside of a swimming pool and they walk in the parallel bars. As they get stronger and stronger, you lower the water in the pool so they bear more and more body weight, so you bring them back to health very slowly and get them used to walking. On this particular case, when we have subjects hooked up to the computer, we have 36 electrodes on the body, and we didn't like the idea of putting them in a swimming pool with 36 electrodes hooked up to the body. So we had to develop our own system. That system involved a sport parachute harness going through nylon straps into the ceiling with counterweights we could add to the subject. The whole system was suspended on a steel I-beam on 18 sets of aircraft bearings, so they could walk back and forth with part of their body weight offset. Initially, when I first put this thing together with my lab people, what I thought would be a good idea would to have somebody walk at moon gravity, at 2/10 body weight. As it turned out, that was a rather bad idea for a number of reasons. The primary one was, every time they tried to take a step, they'd go 3 feet off the floor and hit their head into the ceiling. We began to realize very quickly that the damage from concussion could be greater than the initial spinal cord injury. So we started increasing the weight that they bore until we came up with about 2/3 body weight. When somebody walks at 2/3 body weight, they can walk fairly nicely without hitting the ceiling or jumping off the floor. This is the system then. Sensors located on different parts of the body. And if I could have next slide, please. It's a side view of the system. The microprocessor, like any micro, is just a small Z80 microprocessor in the case with disk drives. Everything else you see in the slide is monitoring equipment, because in fact we monitor in real time every wire going in and out of the body. It's an overkill, but it's a developmental system. We like to be able to record and monitor everything that goes in and out of the body so we can analyze the results. So most of this gear is strictly monitoring equipment to monitor in real time what's happening in the body, where in fact the program and the micro itself are just a small portion of that size. Next slide, please. The initial experiments then were done in this parachute harness support system. Also, the harness had catches on it, so if somebody did fall, before they get within about a foot of the floor, they'd be caught and stopped so they couldn't hit the floor. It's another thing that we don't think about, those of us that can walk. If we trip and fall, we pull our legs out and fall sideways or forward or backwards so we can't hurt ourselves. Someone who's paralyzed has no control. So if they trip and start to fall, they can fall on top of their legs, twist their legs, and break their knees and their ankles. So prevention from tripping is a critical issue for people that are in wheelchairs. This shows a paraplegic subject. You can see the complexity of the wiring. Like the other systems, we had a lot of redundant wiring. And if I can have the 16 on, the 35 off, please. So a lot of redundant sensors, a lot of redundant wiring. The initial program was set up to just have someone stand up under voluntary control and take steps forward. A number of problems in the initial program. The ankle sensors initially were a real problem. We had to put wooden platforms under the shoes to stabilize the ankle sensors. And the control wasn't terribly smooth. There was the principal problem in the system. Notice the left leg, how it drags a little bit. Right leg was moving fine. The left leg, we thought she may have had some neural damage we didn't know about, so we had her go in for a reevaluation with a neurologist. We did a lot of work to try to find out what was causing that leg to drag. The thing that was causing that leg to drag was a spelling error. It took 3.5 weeks to find spelling error in the program. So when it compiled, it was reading the wrong sensor. And it was reading the ankle instead of the knee. So it never really knew what quite to do with the left leg. It just did something until something happened. After that, both legs moved very nicely. And slide on again, please. Next slide, please. Well, from the initial experiments we did to develop these systems, the area that we're working in expanded a lot. All the work that you saw up to that point was done first at St. Louis University and then developed at Wright State and at the Air Force Institute of Technology in Dayton. From that point on, once we knew that we'd done a feasibility study, we'd had computer-controlled ambulation, that there still was a lot that had to be done. The large staff involved with this project in these areas that I'm going to go through very briefly to give you an idea where the project's going, it involves some 16 universities around the world. In Europe, in the United States, in the Middle East. We're working together through Wright State on the problem, trying to develop some of the individual technologies that have come out of closed-loop control so far in a parallel effort to try to make the technology come about faster. We think we can do years of work in a period of a few months if everybody cooperates together and everybody does something slightly different, everybody knows what everybody else is doing, and work together on a common problem. Next slide, please. What we see for the future is a computerized system. Next slide, please. For looking at the body and evaluating the body. That computerized evaluation system would couple patient data from CAT scanners for things like bone densities, neurological tests, and a variety of cardiorespiratory tests to diagnose the level of injury, the condition of both paralyzed and non-paralyzed muscle, and recommend therapy. Next slide, please. This is basically what the system would look like. It would then prescribe therapy on the bicycle and leg trainer system, something we call active physical therapy, prior to the application of a prosthetic device. That is the implantation of a computer chip in the body to control movement, followed by training and therapy. Next slide, please. The active physical therapy system is much different than what you've seen so far in the movies. The final system that we've come up with that we're using really is an electronic physician prescription system. It uses a game cartridge type of a device. Inside of that cartridge is a program. The program itself is carried on an E-squared PROM component, electrically erasable, programmable, read-only memory. The main computer, the physician will sit down at, or a nurse will sit down at, plug the cartridge into it, type in the patient's name, the patient's ID, what his heart rate can be, what his blood pressure can be, how many times he can work out, how much weight he can use, how much torque the knees can take during bicycling, and things like that. The cartridge then stores that along with his program. He then plugs that cartridge into the bicycle, the leg trainer, or in fact the outdoor bicycle. The cartridge monitors his physiology and monitors the work. It also keeps track of the work, and after a certain number of hours of workout, the cartridge dies and stops him from doing any additional work. At that point, he takes it back to his physician, plugs it back into the monitoring station. The computer prints out a graphics printout over time of his workouts, his heart rate, his blood pressure, so the physician can determine again whether he's worked too hard or too little, or to leave the workload at the same level. So it's a much more interactive, physician-controlled system. We think it makes it more palatable to the medical community because it keeps everything under very tight physician's control. Because one of the things we found out very early is that this active physical therapy system can in fact be lethal. If you get someone who's very, very weak and they use it wrong, they can induce a lot of injuries, both to bone and to tissue, if they don't work out properly. So to protect that, the thing is entirely under medical control through the plug-in cartridge system. Next slide, please. To give you an idea of just how fast you can rebuild muscle, down at University of Miami we did a little study. This is a CAT scan printout of the leg. It looks like a round steak because that's more or less what a round steak is from. And the center is the bone in the leg. There's the muscle around the leg. Now this leg we worked out for 15 minutes a day, 3 days a week for 6 weeks. This leg we didn't do anything to. Look at the differences in muscle size. Well, muscle can come back very, very quickly with a minimal amount of workout under computer control. It's an ideal workout type device. We've tried it with non-paralyzed people, with athletes and professional athletes. And instead of going into a gym and wasting your time, the computer control system gives you an absolute, perfectly efficient workout and spot trains muscle very, very quickly. So you can see the differences in leg size. from one leg to the other just with 15 minutes a day, 3 days a week for 6 weeks of workout. Tremendous changes in muscle size and leg blood flow. Next slide, please. Another device we're working on that will potentially help people who have strokes is something called a neural booster. Neural booster basically takes weak neural signals, amplifies those signals, stores them in real time, then re-injects by time sharing the same pair of electrodes. Next slide, please. This is the prototype for the system. And it takes people that are weak and can move a little bit and boost their muscle strength back to normal so they can walk. Next slide, please. For a quadriplegic, the real issue isn't walking. If you go up to a quadriplegic and ask them, what do you want most? It's not walking again, it's using their hands again. Because for a quadriplegic, life is extremely difficult because they can't feed themselves easily. They can't even comb their hair because they can't use a conventional comb. They have to use special combs. They can't pick up a Coke can and drink because they can't grasp the Coke can. That's a critical issue for a quadriplegic and certainly a very easy application of closed-loop technology. Next slide, please. The basic system has sensors from the upper part of the body, and the computer determines in 3 dimensions the position of the shoulders. From those shoulder positions, it determines what the person wants to do with their hand. There's electrodes on the forearm flexor muscles and sensors in the hand to develop the closed-loop system. So the computer knows the position of the fingers and can coordinate movement. Next slide, please. The system's been fairly well tested. It's in a preclinical stage right now. This is a quadriplegic picking up a beaker under computer control. She's a C6, C7 quadriplegic, paralyzed from the shoulders on down. She has some biceps activity to lift her arm up, but all the other muscles in her arm are paralyzed. If I can have the 16 on again, please, and the 35 off. 35 off, thank you. It's an engineering lab. The only thing we had to try the thing out the first time was a wire wrap gun. We let her try taking some pictures with a camera. You can see some wires coming out from under her shirt. We tried a camera. We tried a few things. Now notice when she lifts her hand up and opens and closes her hand. The power's turned off, her hand's paralyzed. Now watch her shoulder. See the slight shoulder movement? That's what's controlling her hand. Sensory input from the shoulder, closed-loop control system with sensors on her wrist, under her shirt, and on the inside of her fingers. The only test that she's failed so far, and we haven't done a repeat on the test yet, is the bagel test. We gave her a bagel with cream cheese on it, which was a big mistake, and every time she grasped the thing, it'd fly across the room. You can see one of the sensors laying on the table. That's a pressure sensor. You'll see more of that in just a minute. Slides on, please. Next slide, please. The bicycle, as I mentioned a few minutes ago, has been redeveloped with a cartridge system. The original bicycle design was unsafe. It was unsafe because in terms of, I suppose, the automotive industry and OSHA, the thing can turn over, it can skid, and a lot of other things. So to make the system safer, we've got differential velocity sensors on the 2 wheels, level detectors, and a variety of other things, an electrical transmission with auto reverse and an electric brake. So the thing is really much more safe. It may be to this point too sophisticated to be marketable, but it's an elegant little bike in terms of engineering. So someplace along the way there's going to have to be some trade-offs if the thing will ever be marketable by anybody, because right now there's a lot of hardware on that bicycle. Next slide, please. Osteoporosis is a fancy name that means bones get thin. One of the things we found out in the studies was that muscle can come back much, much faster than bone. Bone has a very low metabolism. There's not much blood in bone. Bone's a living tissue. But reversing that bone thinness, making the bone come back in a very organized manner so it becomes strong again, is really a very critical issue. Muscle can come back a doubling in strength every month under computer control. Bone only seems to come back 6 to 10% a month. That creates a real problem because you get people that have legs like tree trunks. They're extremely strong, but the bone is still thin. So we had to develop some other techniques of bringing bone back. We tried a number of established techniques. Next slide, please. The one we're working on right now that we've had the best results with is impact vibration. It's something nobody's really tried before. Some colleagues of ours at the university over at Wright Patterson Air Force Base came up with the original idea. And They tried it on osteoporotic monkeys for NASA to find out if using vibration you can reverse some of the calcium loss you get in orbit. And it seemed to work very well. We tried it on people for the first time about 6 months ago. If I can have the 16 on, the 35 off for a moment, please. This is what the system looks like. It's a closed-loop system with accelerometers on the knee so that the amount of vibrations kept constant. And by using that type of impact vibration an hour a day, 3 days a week at 30 Gs, 30 times the force of gravity, 15 times per second, we can get changes as much as 25% increase per month in bone thickness. So tremendous changes. And we feel very strongly now that as we start our experiments over the next few months on geriatric patients, that we may possibly have found a way to prevent bone breakage in people as they get older. If in fact as people get older we can reverse that same osteoporosis and make bones strong, we can do a lot of good for building the body back up again, not only in spinal cord people, but other people as well that aren't afflicted with spinal cord injury. Next slide, please. Next slide, please. Restoring feeling is a real problem also. One of the real problems we've had with our walking system is getting our subjects to trust the computer. They really don't understand what it's doing, what it's about, or exactly which part of the device they're wearing has the computer on it, but they really don't want to trust it because they can't feel their legs. So we're working on several techniques of restoring feeling by taking our electronic sensors and linking those back into the upper nervous system so they get some indication about weight distribution and the position of their legs. Thermal regulation is another problem people really don't think about with people in wheelchairs. People who are paralyzed can't sweat below the injury. So you get somebody who, let's say, is a quadriplegic, you build their bodies back up again under computer control. They're strong again, the bones are strong again, the heart's strong again. You let them loose on the bicycle, it's 100 degrees outside at 80% humidity, they pedal around for a while and they die. The reason they die is they can't sweat below the level of the injury. For a quadriplegic, life is like one of us living in a rubberized exercise suit. So there has to be ways of dissipating that body heat. And by using some Air Force and NASA technology, we're studying that heat dissipation problem, trying to come up with techniques of making sure that body temperature is regulated under electronic control since they can't control it themselves. Next slide, please. Obviously, walking has changed a lot over the last year. The footage you saw was shot about a year ago, and we've done a lot since then. Next slide, please. The first stage for walking for us was developing closed-loop ambulation controls. Certainly, by any means, we weren't the first people to get somebody to stand up with electrical stimulation. Open-loop control has been used since about 1962 to allow paralyzed people to stand up and to swing their legs forward and take a few steps. But closed-loop control and developing that closed-loop control has been a real problem over the years. We accomplished that about a year ago. Over the last year, we've been working on balance, obstruction clearance, and making the system portable and wearable, getting ready to come to a point where we can surgically implant the system sometime in the future. Next slide, please. These slides show some of the current experiments in the system. Notice that now we don't use the safety harness anymore. And this particular point, we still had a lot of the wiring. This paraplegic subject, at this point, is walking on using wooden canes. We had parachute boots originally for the subjects. The reason we used the parachute boots was for ankle support. The ankles are, by and large, the worst part of the human anatomy after spinal cord injury. The bones in the ankle and foot take on the consistency of very thin mashed potatoes after about a year of spinal cord injury. So having somebody stand up for the first time on that ankle can crush the ankle into powder. So to keep anything from happening to the ankles, we went to parachute boots for good ankle support. Next slide, please. This shows some of the standing experiments. Notice the balance. I'll show you in a minute how we get the balance. She can take both her hands off the bars, stand there fully supporting her body weight with no problem because she has balance. She has an electronic inner ear hooked up to the microprocessor. Next slide, please. This shows some of the walking. Again, notice no support harness and how little activity she has in her upper body. She's just using the parallel bars for guidance. Next slide, please. Next slide, please. This is a quadriplegic standing up. And you'll see some footage in a minute of that. The problem for a quadriplegic standing and walking is immense. With all those paralyzed muscles, it completely taxes the computer system to the limit of what it can do in real time. Next slide, please. The system itself was miniaturized for outside type use. The computer can be worn on the belt. There are sensors on the hips, knee, and ankle joints, and in the feet to show the computer the position of the body in 3 dimensions. The thing that I said I was going to show you a little bit later is these level detectors, and I'll show you pictures of those in just a second. They're from ICBM missiles. They're about the size of a dime. They're used to correct gyros. Those small level detectors, there's 4 of them on the body, provide the same type of information the body gets from the inner ear. And that information is used for balance, so that there's, in software, balance-catching subroutines. As somebody starts to trip, the computer moves their legs around to find balance, reassess gravity vectors, and bring their body back up to the standing position again. Next slide, please. This is one of those sensors. You can see the size of it. It's encapsulated, or encased, I guess, in an aluminum framework for protection. The device itself can be surgically implanted, runs very well with approximately 4 volts at 6 milliamps total power. Next slide, please. This is the current size of the computer. You can see it in relationship to the hands on the slide. It uses a Z80 microprocessor. The rest of the device are timers and memory, both EEPROM and scratchpad memory, to enable the device to interface with the body. Next slide, please. This shows the device in operation outside in the university. Notice there's far less wires. A lot of the redundant systems were taken away. Also notice there's no tape on the electrodes. Those are a new generation electrode developed by 3M. There's no tape, no electrode paste. You pull them off, and when you push them on the body, the harder you sweat, the harder they hold. They have a consistency on them that feels like snake skin. It's kind of cold and clammy. And they're self-adhering and permanently gelled. And with those using external skin type electrodes, you can put all the electrodes on the body in a few minutes and have the wires hooked up to the computer. Obviously, this isn't the way we're going in the future. As a temporary measure for testing out control systems, it works very well. As a permanent system, we're working on a surgically implantable system to go inside the body with a microprocessor chip that would go in with the wiring. Next slide, please. One application of this system, and if you could focus that just a little bit, please. One application of this system was last June. The particular girl you've seen in these last few slides, could you focus that just a little bit, please? Great, thank you. The girl that you've seen in the last few slides is a paraplegic. The last time she walked in public was at her high school graduation. So she wanted very badly when she graduated last June to walk to her college graduation and get her diploma on her own feet. And she hadn't walked really publicly in about 4.5, 5 years. So we used the small portable system, held her hands for support so she couldn't fall, and let her walk up and receive her diploma for her graduation. And I can have the 16 on again, please, and the 35 off. You notice in this sequence now that the support harness is gone, and she's standing up under computer control. It's far less wiring. In this particular clip, she's using tennis shoes for walking. You'll also see some plastic supports on the back of her ankles. Those are for ankle support. We hope to get those off sometime over the next year, as soon as we know our ankles are back to normal thickness and can hold the load properly. Now, just as we do in the morning, when we stand up in the morning, we stretch a little bit before we can walk properly. People that are paralyzed, we found, have to do the same thing. They have the muscles are a little bit stiff, they have some spasms. When they first stand up at the beginning of the day, they stretch a little bit. Notice as she keeps stretching how better, her balance gets better and better to a point where she can just stand there very freely. One of the trade-offs we've had to make up to this point with the stimulation system we're using is that since we're using electrodes on the surface of the body, we really can't get some of the deep muscles. So we have them bring their leg back a little bit before it goes forward to provide enough momentum to carry the leg forward, because we can't get at some of the deep hip flexor muscles to lift the hip up from the surface of the skin. When we go to an implantable system, that'll change things a lot. But for right now, we can't get to the muscles to lift the hip up more than a few inches, so we have them bring their leg back first and then swing forward, since the muscles to bring the leg back are located on the surface of the back of the leg, and they're easily accessible with surface electrodes. One of the things that we found out that was interesting is people walk backwards better than forwards. The hip joints and the knee joints lock in the backwards position, so it's really easy to walk backwards. If we could get people to walk backwards, we'd be through in terms of the research, and we could have paralyzed people all over the world walking again. Walking forwards is really tough. But you can see how much better the control is there than the original sequence. In fact, it's gotten a lot smoother since then with the small portable system. We still use the laboratory system as a developmental system for testing out software, then transfer that software onto the portable system. This is a sequence standing with canes. You can see how little effort that she has to use to stand with canes. With walking, if we have her walk with canes, she tries to lean on the canes and use her body strength to move. She doesn't really trust the computer. If I take her hands, after she's taken about 15 steps, she'll shove one of us away, and then she'll take her fingers and just touch two of my fingers with her fingers and walk along very nicely. As long as it's another human being, she'll trust the computer. But if instead of using us, we give two wooden canes to her, she will not trust the system yet. So that sensory feedback is very, very important, because if she can feel her legs, she'll begin to trust the computer system. This is a quadriplegic. Notice how hard it is to stand up and the balance problems you have. Some of the weight's offset here. And the quad's in a support harness, approximately 1/3 of her body weight offset. She can do very little in terms of holding onto the parallel bars because she has no hand control. She can lean on the bars, and that's about it. This is an initial sequence in the lab starting to learn how we go about getting a quadriplegic to walk. And it's going to be some time before a lot of those problems are resolved. And 16 off, 35 back on. Next slide, please. Well, the computer system that you saw, the portable system, allowed us to gain a lot of insight into what's going to be happening in the future in terms of our research. The system now is small, very lightweight. For battery power for the surface of the skin, we're using a photographer's battery belt. The system itself uses level detectors, but it still has a lot of wires connected up to the body. The computer system you saw for graduation enabled one of our paraplegic subjects to walk up, give about a 3-minute speech, receive her diploma, and sit down. And there was still very sufficient battery power left to have her walk around for another few hours. But there are a lot of problems in terms of wiring for an external system. One of the ways we're thinking of getting around that has to do with some new technologies that have become available to us. This looks like a pair of pantyhose. In fact, they're made by legs, but they're made out of conductive yarn. That yarn can be woven into patches of conductive and non-conductive areas, and what we're trying to do is stimulate the skin through the pantyhose. So you have a little wiring harness coming out of the side of the pantyhose. You pull the pantyhose on, and that's all the electrodes in place. Next slide, please. For sensors to sense the position of the joints, we're using something developed by a university working with us in Glasgow, Scotland. These sensors are made out of an elastomer material. They can be sensitive either to stretch or pressure. They can be made the size of a thread. Over the physiological frequency range, there's very little, if any, hysteresis, and they provide a fairly linear output in terms of resistance, which changes in position or pressure. We've used these in a number of systems. The first practical use of those sensors was the hand control system. Those elastomer sensors were woven into the quadriplegic you saw. We had those woven into her bra. So when she moved her shoulders up and down, forwards and back, the elastomer sensors provided an output for the computer as to the shoulder position, which was decoded then to move the fingers and hand. Next slide, please. So we have really a long way to go. I think over the last 13 years, we've come a long way. It's still a research project. Some of the elements of the project are going to become available to the public fairly shortly. The university, since we're a state university, we're not allowed to get into the manufacturing business, has licensed out the bicycle system and leg trainer system to a commercial manufacturer who hopes to have those on the market by about next summer. So those devices will be becoming available to everybody in wheelchairs. The hand control system should follow in about a year. The walking system is still going to be a long time away for either an external system or, in fact, an implantable system because of all the problems associated with balance and systems reliability and making sure the system can function without doing any damage or any harm to the subject. That's basically where we're at and where we're going. I'd like to thank you again for your time in coming here this evening. and for the invitation to come up to see Digital Equipment Corporation and the museum here. If you have any questions, I'm more than happy to answer them. Thank you. Yes?
Could you explain again why, when you want to build up the muscle, that by doing it by firing the electrodes, the neurons, why that's better than just, say, you moving it, a physical therapist?
Oh, really simple. Well, in terms of a paralyzed person, a physical therapist moving the muscle doesn't cause anything to happen in the muscle. They're just passively stretching it. When you fire the muscle electrically, it causes the metabolism in the muscle to go up. That's a genetic clue to the inside of the muscle. When it loses energy stores because of being used, the genetics turn on in the muscle to start generating increased muscle mass, to increase the amount of blood going through the muscle, and to increase the metabolic capacity of the muscle.
Does any good thing happen physiologically then when a physical therapist does?
Yes, absolutely. When a physical therapist moves the legs and arms passively, it increases or maintains what's called range of motion. And all you mean by that is that if you don't keep moving the limbs, calcium will form inside the joints and freeze the joints up. That's what's good with the passive physical therapy. Also, it keeps adhesions from forming in the tendons and muscle to keep everything nice and loose. But in spite of that, bone gets very thin. And in fact, a number of the physical therapists I know, for example, tell me that it's a fairly common occurrence for them to be lifting and moving somebody's leg who's paralyzed and have a leg break during passive physical therapy because the bone's gotten so thin. Actually making the skeleton move again under its own control bends the bones, causes bones to become thick in ways that you couldn't do with passive physical therapy. In terms of an athlete, it's a totally different issue. With an athlete, moving the arm from here to here, you use several different muscles. And you can't really very easily control which muscle you're using to build things up properly. For example, if the muscles on one side of your leg are slightly built up more than the other side, if you go under heavy stress, it puts a shearing force across the knee and can cause a knee injury. With electrical stimulation, you can spot train individual muscles and bring those muscles back individually and make them much stronger than you can with weightlifting, because you can do one muscle at a time. Mm-hmm.
Can I get rid of my paunch by doing the equivalent of sit-ups?
Yes and no.
To
Yeah.
get sponsorship.
Pardon? No.
The way to get sponsorship.
No, you can do it, but in terms of sit-ups, it would take so many sit-ups. The thing that's depressing about jogging is you have to jog roughly 8 to 12 hours to lose a pound. You lose a lot of sweat, but then you drink water and it comes right back again. But if you measure the number of calories you're burning, it's very depressing, the amount of work you have to do to lose weight. Yes?
Does the medical technology exist to have a lot of wires going in and out of the body for implanted electrodes? What's the story there?
Yeah, there's two ways of doing it. One way, for example, for stimulating the brain is to use a printed circuit type matrix, where you can have hundreds of wires interfacing with the body. That's done for the artificial eye experiments that are going on and for some of the sensory experiments going on, for example, at the National Institute of Health. In terms of wires going in and out of the body, the most common way of doing it is multiplexing, the same thing you do with a space capsule with digital hardware. You have a small CMOS device under the skin. The wires from there run to every place you want to have them go to. Then you multiplex on a single channel through the skin, RF coupled, what you want to have turn off and on it, when, and by how much. And that's very common technology, and in fact, that's commercially available. The thing that we don't have at this point that you can put inside the body is sensors. And we have great hopes for our elastomer sensors being the first sensors you can they're sufficiently safe to implant inside the body. They're non-toxic. They're not rejected by the body as far as we know from animal experiments that have gone on with them. They can be sewn to tendons to show tendon position and muscle position. So they've been tried out in lab animals now. We hope to get to that in people sometime very soon if we know those sensors will last for a long period of time. So the longevity of the sensor is the key issue right now for us. You don't need that much. All of our work that was done with closed-loop control in animals was done with an electrode array. It operates something like the beam on a CRT scanner. I guess I nicknamed the thing when I published it the first time, focus field electrode array. And it uses about 15 wires around a silicon electrode on a nerve and scans the nerve to select which nerve fibers it's firing. Well, that whole electrode array, to tetanize a muscle, to get a good strong contraction, takes 1/10 of a volt at an average current of 1 microamp. So the power inside the body is very low. The problem you run into is when you stimulate on the surface of the body with electrodes, because you've got to get those currents through a fat layer. Well, fat's oil. Oil is a heck of an insulator. So you have to use very large currents on the surface of the body when, in fact, not much is getting into the nerve. It's just that you've got an electrical insulator you're trying to stimulate through. So once we go inside the body, power is not a problem anymore. Mm-hmm.
Could you tell us a little bit more about the dialogue that you have with other researchers in terms of mixing up the various kinds of research that's going on and collaborating?
Basically, the other people working with us, the question was about the type of dialogue going on with different universities. Different people are doing different things. What we found is different people have different expertise in certain areas. For example, University of Nevada is cross-comparing CT scans with bone biopsies to find out how reliable we can be with a CT scan in determining how dense bones are. We've got basically a real problem. Everybody tries to consider bone density equivalent to bone strength. In fact, that really may not be the case, because where the calcium's laid down and how strong the matrix is inside the bone may be the determining factor in how strong a bone is, not how dense it is on X-ray. So we've been doing a two-dimensional, actually a three-dimensional CT scan of bone, and there's been very few people that have done that, looking at the bone matrix and bone density. We take 10 slices. Each slice is 1 millimeter of bone across the leg. Each slice generates about 25,000 pixels. Each pixel is 12-bit resolution. And we're trying to visualize in 3 dimensions the bone and cross-correlate changes in the density of that bone to change, and where the density is located, the changes in bone strength, so we know exactly where we're building bone up and by how much. So University of Nevada's orthopedics department wanted to do bone biopsies, so they actually take little pieces of bone out and correlate that to what we see on the CT scanner non-invasively. So the rest of us working on the project can have a better database and greater reliability for CT scans. That's their little piece. University of Miami had some people that are fairly good, for example, in muscle biopsy. So they've been doing muscle biochemistry studies for us with leg trainer and bicycling. Nevada's doing leg trainer and bicycling with bone biopsies. So different people do different things. I'm involved, for example, with Dr. Nathan at Ben Gurion University in Israel, helping him in his project. And what he's doing is trying to get hand control in people that are paralyzed from the neck down, very high-level quadriplegics. They can't move anything. They can just talk. And we're using voice decoding and then ultrasonic sensors on the fingers and hands, so when they say drink, the sensors visualize the glass, find the glass, go to it, move the arm out and grab the glass and bring it up to their lips. So that's really a much more sophisticated project in multi-dimensional hand control. So different people do different things. Mayo Clinic's involved in the psychological aspects of the problem. How does it change somebody's self-image? We get a big change in psychological profiles when people become part of the project. They behave differently, they dress differently, a whole different attitude on life. Most of our quadriplegics, as soon as they start getting built back up again, get rid of their electric wheelchairs and go to manual wheelchairs. They just don't want to be involved with an electric wheelchair. They don't feel paralyzed anymore because their legs are normal size, they're the normal color, and all the girls in the project wear shorts around all the time on campus, even in the wintertime, because they like the way their legs look. So there's just a lot of people working on different things. Everything's coordinated, I guess, through myself and through Dr. Phillips, my co-investigator and the vice director of the center, so that nobody really wastes anybody else's time. Everybody's doing something different that's necessary for the project. Yes?
How have you selected the patients that you're using?
Tough question, really. The question was, how do we select patients? It's based a lot on our needs for a particular study. We found out some things really kind of interesting. It's, in terms of our research, kind of a flop. In terms of I guess, therapy, it's not a flop at all. It's a very good pro. The neural booster so far has been a total disaster. The neural booster is the thing to boost muscle strength, because the 3 people, well, 2 people in particular that I brought in to date and to be subjects who had very weak muscle activity. When we started building their legs back up, one girl in particular hadn't walked in 9.5 years because her muscles were just too weak. It was a partial spinal cord injury. When we started building them up on the bicycle and the leg trainer and everything, they got enough muscle strength back. They didn't need the neural booster. They could stand up on their own. So it blew the neural booster study because they walked out of the lab without anything. Those devices really do build the body back up again. So different subjects are selected for different things, and they're also selected in terms of psychological profile. Most of the people in the lab had things on their discharge records written. For example, Nan Davis, the girl who walked up to graduation that you saw on the slides, had written across her discharge records that she was a troublemaker, wouldn't accept being paralyzed, and kept telling everybody she was going to walk again. Well, that's basically the mental attitude of most of the people in the project, because this is very tedious, long work. When we first brought the walking system up and brought it into operation, we were doing, between 24 and 40-hour experiments. Try something out, software didn't work right, go back, change the software, do a simulation. We had a department store mannequin, and we do a simulation on the mannequin, check all the joints, check it out for the tripping subroutines and everything. Everything looked okay. That'd take about 12 hours after we make a software change. We'd hook Nan back up again, try it out again. It wasn't quite what we wanted. Go through another 12 hours of tests. And those would go on for between 30 and 40 hours. We'd take 4 to 6 hours off and go back at it again. Because once you've got the program in your mind, you can't go away for 2 or 3 days because you'll forget where you were in the software, which is fairly common, I guess, for software people. But in this case, it's not just a software people. This is a whole lab of about 15 people working 30 to 40 on and 4 to 6 off for about 3 weeks to bring the walking system up. And for that reason, not just for our lab personnel who are extremely dedicated, but for the subjects, they have to be go-getters. Because unless they're willing to put up with that type of nonsense without really understanding computer people and what motivates computer people to sit in front of a terminal for 3 days, they have to be in there willing to put up with that. In fact, Nan felt sorry for us, so we taught her how to solder, and she soldered a lot of her wires together on the wiring harness while we were working on the software. Mm-hmm. Yeah, we think it will. I've got a colleague at Tulane, and we've been looking at the fact that we have a problem in this system. People in wheelchairs get spasms. And if they stand up and get a spasm or get a spasm on the bicycle, it can be very dangerous. It can really mess up walking if they get a spasm while they're trying to take a step. So the system has a 3-dimensional profile in it of what they should be doing when they're walking in real time. If there's any wide deviation from that system, then it detects spasms, that it's stimulating and something's moving the wrong way. So what it does is it goes in and physiologically breaks up the spasm by stimulating other muscles that inside the spinal cord will break the reflex up. So our system autocorrects for spasms and breaks them up. We think for cerebral palsy we can do the same thing, not by breaking it up through the cord, but by electronically blocking muscle. You can use electricity to stimulate a muscle, or you can use it to paralyze muscle. So a colleague of mine that we're working with at Tulane tried it in terms of the nerve itself, and he can paralyze the muscle by rapidly stimulating the nerve at the right frequency with the right type of stimulation. We're trying to do it through the surface of the skin, which would be much easier than doing surgery on people. But if everything matches and works properly, yeah, I think we can do something for cerebral palsy by looking at walking profiles and stimulating muscles that aren't working and paralyzing instantaneously others that come in at the wrong time. Yes?
In terms of the software that you're using, are there any investigations, or have you taken advantage of any of the artificial intelligence or the so-called expert systems?
Yeah, they scare me, though. The trouble with those systems is you can't follow them when they're running. And I need to know exactly what's happening in that program so that I can make changes in the hardware and software, because this is it's a fairly complex hardware-software system. I think the way of the future is to use an artificial intelligence system. For right now, I need to have a very good, thorough knowledge in my head of everything the program's doing. And with an AI system, sometimes you just don't really know what it's doing in real time. So for right now, I'm using it's a learning tree type of system. It goes through logical decisions. The program does rewrite itself, and it does make some decisions, but it's not really an artificial intelligence system because you can find out what it's doing and follow the thing. but it does change constants. For example, when somebody stands up, it allows the knee to wobble 10 times. Over that 10 times, it looks at control voltage versus movement, then makes a decision about what it's doing right or wrong in terms of a logic tree, and then readjusts the program to get better control of the knee. Then every certain amount of time, it re-looks at the knees and the ankles and so on, then modifies its program on basis of muscle fatigue or whatever. Yes?
Do you have any cooperative sensors in the New England area?
Not right now. We were site visited down at the university by Massachusetts General Hospital, who want to get involved with their gait lab with what we're doing. I was supposed to come up about 3 weeks ago and give a talk, which was unfortunately was on a Wednesday, and my wife's expecting in 3 weeks, and I have to go to Lamaze classes every Wednesday, and we've been, if I came up here, so I put it off for about 6 weeks. So I hope we'll have something going by Christmas, but it's temporarily on delay until the baby comes. Wednesdays are taboo for trips.
Is the center funded as a national center by somebody?
Yeah, a number of different groups, different spinal cord groups, also by the Veterans Administration, very heavily by the Veterans Administration. It's been funded in the past by the National Institute of Health. Actually, it's also been funded very heavily by Air Force, Army, Navy, and NASA. You may wonder what the connection is. I didn't really think of the connection. It came to me instead of me coming to it. I gave a poster session back in 1976 in Chicago at a national meeting showing decoding the thought process using the electrical activity from muscles to determine what a person wanted to do and how fatigued they were getting. I didn't really think about the applications of that to the Department of Defense. And I guess most of our funding over the years has come from the Department of Defense on decoding the thought process.